Hello, welcome back to the second lecture of week 2. So by now, we should be able to analyze the time efficiency of an algorithm by investigating its sequential instructions, conditional instructions, and loops. So next, we'll be spending 2 lectures learning how to analyze the time efficiency of recursive algorithms. Okay, so let's get started.
Recall that we also learned another sort algorithm, merge sort. We know merge sort is a more efficient algorithm comparing to insertion sort. So now we'll be spending 2 lectures investigating the time complexity of merge sort and recursive functions in general. Now we review how merge sort works. In order to sort list A, we divide A into 2 equal-sized sublists, sort these smaller lists, and combine them into one sorted list. We can use recursive calls to sort the smaller lists. How to merge 2 sorted lists? Say when we already sorted A left and A right, how can we combine all their sorted items? Think about how we would do it by hand, and then we can translate that into an algorithm. Imagine we have 2 sorted decks of poker cards, and we need to merge them. We look at the top 2 cards from the 2 decks, see which one is smaller, take that one. Then we compare the 2 top cards again and take the smaller one. We repeat this process until one deck is exhausted, then we take all that's left in the other deck. So the same idea here for merging the 2 sorted lists. We scan A left and A right from the smallest to the largest and save the items one at a time to a new list. We put 3 down first, then we compare 27 with 9. 9 is smaller, so we put 9 down, and so on. We can formalize the idea of merge sort as this. We divide the input list A into 2 equally sized sublists. We recursively call merge sort to sort the sublists. Then we merge 2 sorted sublists. Here is a graph demonstration of how merge sort works. The recursive calls essentially split the lists into 2 equal halves every time until we have only sublists of individual items left. Then we merge 2 of them at a time and reconstruct the entire list with all original items sorted. You may also notice that merge sort goes through these exact steps for any inputs. So it does not matter how sorted the original input lists are, its running time will always be the same. That is, the best case, worst case, average case, any case complexities of a merge sort are the same. Here we have the pseudocode algorithm from the textbook for merge sort. A is the input list, and P and R are the control indices we can use to specify which sublist of A we're operating on. We find the middle index of the sublist, recursively call the merge sort function twice on the 2 equal sublists. Last, we call the merge function. Based on the idea we discussed before, we can write this merge function that combines 2 sorted sublists into one. So first we get the length n1 and n2 of those 2 sublists. We create 2 new lists or arrays, L and R, and copy all the items to the 2 sublists into them. We set the last item in L and R as an infinitely large number in order to signal us reaching the end of the lists. Then we rewrite list A directly from index P to index R. We look at both L and R and pick the smaller one and write it to A. Now we have all the components of merge sort figured out. Back to our original question, what's its complexity? First, what is the complexity of this merge function? We have 3 loops, all single layered, so it is not difficult for us to find out that its complexity is big O of n. In fact, it's also theta n. So what's the complexity of merge sort? T of n. So we know we need to run merge sort twice with half of the input size. And also we have the merge function, which takes theta n times. So how to figure that out? What is Tn? It's not a closed form because we have Tn over 2 in its expression. Let's take a step back and start with some simpler recursive algorithms. In this function an, it is recursive. Now we know. Each time we call the function itself, the input reduces by 1. Although we know this function does not contain any loops, its running time still grows with the input size. We know A7 for sure runs longer than A5. We ask ourselves, can we write the running time as a function of the input size? What is their relation? So now let's write this relation. We know all recursive functions need to define a base case or base cases. Otherwise, the recursive function will keep running until the recursion limit has been reached and get an error. We assume the input is a non-negative integer, so the base case would be when n equals 0. We can write Tn would be just a constant when n is 0. When n is greater than 0, we know that Tn is C2, there's some constant time, and then we can cover any sequential instructions other than the recursive calls. And then we have the recursive call, and then the input size will be reduced by 1. Now we have the recurrence relation for an. It does not seem that we have the answer since we still have the term Tn minus 1 in Tn's expression. How to get rid of it? Now we introduce the method, expansion or substitution. Given this recurrence relation, let's write this relation in a more general format using x. So x can be any value, could be n, could be n minus 1, n minus 2, could be 3, could be 2. Now we can write Tn as C2 plus Tn minus 1. Now we want to get rid of this. Okay, so using this more general form, we know that when x is n minus 1, we know Tn minus 1 would be C2 plus Tn minus 2. And we can use this to replace Tn minus 1 here. So we get C2 plus C2 plus Tn minus 2. And then we can also replace Tn minus 2. So that'll give us C2 plus another C2 plus Tn minus 3. And then we write C2 plus C2 plus C2 plus Tn minus 4. So we keep writing this until in the end we get a bunch of C2s. We get to Tn minus n. So that would be T0, and we know that T0 is C1. That's the base case. So finally, we can get rid of all the T's in the expression for Tn. So now the question is, how many C2s do we have? But let's see the pattern here. So when we have Tn minus 1, we have 1 C2 here. When we have Tn minus 2, we have 2 C2 here. When we have 3 here, we have 3 C2. We have 4 here, we have 4 C2. So here, this is n, so we have n C2. So now we know the final form would be n C2 plus T0, that will be C1. So that's the closed form of Tn. And we also know now this belongs to theta n. Now we can have this summary table to include the complexities of different recurrence relations we see. In fact, many algorithms or functions fall into a small set of common recurrence relations. We will see more examples and add them to the table. So in the future, we'll be able to know the complexity of a recursive function very quickly. Now the second example, function b. What's the recurrence relation for b? Please pause the video and try writing it down. Okay, did you get this recurrence relation? The base case is when n equals 0. When n is greater than 0, Tn would be C2, the cost of any sequential instructions that could be included in B, plus C3 times n, the cost of implementing this for loop, and Tn minus 1, the cost of calling B with input n minus 1. Now, how to use substitution to derive the closed form of Tn? Write Tn using the substitution. So that's C2, C3 times n plus, so we replace Tn minus 1 with C2 plus C3 n minus 1 plus Tn minus 2, right? Because we know Tn minus 1 would be C2 plus C3 n minus 1 plus Tn minus 2. Okay, so once that's clear, we can rearrange this a little bit. So we move all the C2s together and we have C3. So that's n plus n minus 1 and Tn minus 2. And we can further replace Tn minus 2. So that'll give us C2 plus C3 n minus 2 plus Tn minus 3. Okay, we can rearrange a little bit. We have a bunch of C2s, and we have C3 here, n plus n minus 1 plus n minus 2. So now we know if we just keep writing this, in the end, we will get a bunch of C2s, and we'll decide how many C2s we have. And then we also have C3, and then there's a really long term here. We'll decide what this is. And then in the end, we won't get to the base case. So that's Tn minus n. So that'll give us T0, and we know that's C1. So now the question is, how many C2s we have? And what's here? So now let's check the pattern. When we have 2 here, we have 2 C2. When we have 3 here, we have 3 C2. So when we have n here, we have n C2. Okay, so what about this term? So when we have 2 here, we have 2 terms, starting from n to n minus 1. When we have 3 here, we have 3 terms. So when we have n here, we would have n terms. So that gives us n plus n minus 1 plus n minus 2. So we write n terms. So that'll get us to 1. Okay, so now we know in the end we'll have n C2 plus, so what is this? 1 plus 2 plus 3 plus all the way to n. So that'll be n minus 1 over 2 C3. And then we have the last term C1. Okay, and then we can observe that the highest order term would be n squared. So we know the complexity of Bn is in theta n squared. Again, we add it to the summarization table for a quick lookup in the future. After this lecture, try and derive the complexity of the recursive binary search. Okay, this will be all for this lecture. So what about merge sorts? We have done some preparation work in this lecture, and we will get to merge sort in the next lecture. Stay tuned.